Now we are going to complete the notes on Rolle's and Mean Value Theorem. So title it Rolle's and MVT Part 2. This will be short. For example, explain why the following fail the MVT hypothesis. ... I am going to give you two equations that are purposely going to fail the MVT hypothesis, and I want you to see if you can figure out why. Okay? We're going to actually do them together. First one, f of x is equal to the square root of x squared, and then outside the square root plus 1 on the interval from -3 to 3. I want to know why this thing fails the hypothesis of MVT. Now, MVT has two parts to its hypothesis. The function has to be continuous on the closed interval, and it has to be differentiable on the closed interval. Okay? Now, in this case, is it continuous? Okay, in other words, am I allowed to plug in anything I want to for x, and will I get an answer? Could I plug negative numbers in there? Yeah. Can I plug positive numbers in there? Yeah. Plug in 0? Yeah. Is there anything I can't plug in physically? Yes. Question?
No. Well, because isn't it when you take, like, how do you get imaginary numbers from that?
You can't. That's the point. Because when you square it, if you put a negative number in there and you square it, it'll be positive, and then you can take a square root and you're okay. Yeah, that was what was bothering you. So in this case, everything is fair game, and that's how you tell if it's continuous or not. If everything's fair game, it's continuous. Check. So if this one's fine on the continuous front, it's got to have a problem on the differentiability front. Okay. Now here's the ability front. Let me show you this. What does the square root of x squared equal? It does not equal x. It equals the absolute value of x. Stephen, can you explain why it's absolute value instead of just x? If it's a positive, okay, that is a very simple way that you were right. If it's a positive or negative x, it'll always come out positive. If the answer was just x, that means that no matter what you plug in, you will get the same exact thing out. So if I put a 2 in here, would I get a 2 out? Think about it. If I plugged a 2 in for x, would I get a 2 out of the radical only? Yes. If I plugged a 2 into that radical, I would get a 2 out. If I plugged a negative 2 into that radical, would I get a negative 2 out? No. I would get a positive 2 out, wouldn't I? So plugging in negatives give you positives. Plugging in positives give you positives. That's why it's absolute value. Okay? Plus 1. Now, why is this now a differentiability problem? Who can tell me? What did I just talk about? Can you take the derivative of an absolute value? No. Is there a point on absolute values where it's not differentiable? Yes. Where? At the sharp corner, exactly. Now, for this problem, where will the sharp corner be? No, that's the y value of the sharp corner. What's the x value? Turn it around. 1. H is 0, k is 1. So it's at the sharp corners at 0, 1. Is 0 between here? Yeah. So this one is not differentiable at x equals 0 because it has a sharp corner. That's why it fails. Okay? So, was it continuous? No problem. Is it differentiable? No, because it has a sharp corner at 0, and 0 is on the interval. Okay? Questions? Okay, part B. F of x equals x squared plus 3. X is less than or equal to 1. X squared plus 1. X is greater than 1. We're going to go on the interval from 0 to 2. Okay. because I did not do problem 16 with you in here. We need to have a very important conversation about this problem, okay? Now, how can you tell if a piecewise function is continuous? We're going back to first 9 weeks. The right-hand limit has to equal the left-hand limit has to equal the point. Okay, so we need to test continuity by doing that. X squared plus 3 by itself is fine. X squared plus 1 by itself is fine. But the question is, do the pieces meet? Okay, and that's going to be the question of continuity. So is it continuous? I don't know. So we're going to do the limit as x approaches 1 from the left of the function, and the limit as x approaches 1 from the right of the function. Okay? Now, I didn't draw my little number line, but hopefully we're getting to the point where we don't need it. I'm going to wait just a minute because I see lots of people scrubbing. No, it's not. If you like the number line, let me just go ahead and do the number line because there's going to be people who need it. What number goes on it? 1. Which equation is to the left? The first one. To the right is the second one. So they happen to be in order. Kind of helps. So for my first limit, which equation am I plugging into? I'm plugging into the first one. Plugging in 1. What do you get? 4. So that one's 4. For the second limit, I'm plugging into the second equation. I'm plugging in 1. What do I get? 2. Is it continuous? No. Therefore, it is not continuous at x equals 1. So that's where it failed. I shouldn't have boxed that because that looks like it's a candidate. That's where it's failing in the mean value theorem. Okay. Now, because we did not do 16, let me go ahead and talk about this as well. Let's say that 1 worked. The limit from the left was equal to the limit from the right, and the dot was there, and everything was good. How would you go about testing differentiability? The derivatives from either side, okay? And this is the only possible place, listen carefully, this is the only possible scenario where a derivative could fail without having a denominator. You hearing me? What did we always say before? Derivatives fail when you have denominators with x's in them, except for piecewise functions. Piecewise functions can fail here. So what you would do is if you had to keep going, you would take the derivative of both of these, plug in the 1 on both sides and see if that worked. If that works, you're good. If it doesn't, then it's not differentiable.
Plugging the 1s to the derivative?
To the derivative, yes. So if you're testing continuity, you plug into the original. If you're testing differentiability, you plug it into the derivative. Okay? I think that kind of went over some people's heads. Are y'all with me? It's Friday. I know. It's hard. Okay. So, now, the last thing I want to do with you guys, and you're going to have a lot of time to work, I'm going to do number 15 off the Rolle's theorem worksheet with you. Okay? And this is an interesting real-world application of the mean value theorem. I am going to fold my paper so you can see it. Let me fold it a little bit farther. Oh, that's good. So you can see the problem right here. I'm actually going to, I don't know. Let's pull down a little further. Now you can just do this on your notes and then transfer it later. That's fine. Okay. Yes, ma'am. Yes, please. I do want the Rolle's theorem done on a separate sheet of paper. Okay. Now, if you have the worksheet, you can follow along. If you don't, you can just look up here. It says that a trucker handed in a ticket at a toll booth showing that in 2 hours the truck had covered 159 miles on a toll road in which the speed limit was 65 miles an hour. And the trucker, even though they didn't catch him speeding at that moment in time when he stopped, was given a speeding ticket. How could they do that?
Do they have like put the money or whatever?
Okay. Nope. So this is a way that you could actually get a speeding ticket without being caught in the act of speeding. That's an interesting concept, okay? Let me show you how this works. Please write down the mean value theorem formula. F prime of C equals F of B minus F of A over B minus A. Okay. We have talked about this in terms of slopes of lines connecting A and B equal to the slope of the two lines at C. But I want to talk about it today in terms of rates of change. Okay? Because it has an application in the real world. The right side of this formula, what formula is this?
Average rate of change.
Average rate of change. So this is the average rate of change from A to B. And what is this side of the equation? If this side's average rate of change, this side is what? What kind of rate of change? Instantaneous. This is instantaneous rate of change at C. Okay. Now, I think once I do a little bit of math, that the reason this trucker got a speeding ticket is going to make a lot more sense. Okay. From what the problem tells you, could you tell me his average speed on that 2-hour trip on the toll road?
79.5 miles per
Right.
hour.
So the
Which
truckers...
already is irrefutable proof that he
Right.
was speeding at some point.
Exactly. The trucker's average rate was calculated to be 159 miles in 2 hours, which is 79.5 miles per hour. So I don't know exactly how fast he was going at every moment in time on that road. But I do know for a fact that he had to go an average speed of almost 80 miles an hour. And according to this formula, the average rate of change, which in this case is 79.5, has to equal his instant speed at least 1 point on the interval. He had to have been going at least that fast at least one moment in time, according to the mean value theorem. Now, how many of you can see that in your head already? You can see the fact that he had to have been going he had to have gone over 65 miles an hour at least once in there. Are you seeing that or not? If his average speed was 80 and the speed limit is 60, he definitely sped sometime. It's kind of a logical thing if you think about it.
Cops should have to work to give you tickets. That should be illegal.
He's doing math work. Think about it. Okay. This proves it. This proves it.
Yeah, my dad got one.
Did he really?
Yeah.
Okay, so the mean value theorem says that the trucker's instantaneous speed had to equal his average speed at least once on the trip. That, therefore, he had to have gone more than 65 miles per hour. So that's basically the answer to that question. You're going to write all that down. Mean value theorem says that the trucker's instantaneous speed is equal to his average speed at least once on the trip. That's what the theorem says. Therefore, he had to have gone more than 65 miles an hour because he had to have gone at least 80 at least once. Probably went 80 or maybe even 90 for part of the trip. You know,
That's slow.
in a big rig? I don't think I want a big rig going 90 miles an hour down the road. I've ridden with my cousin who was a trucker in his truck for a drive from Waco to Houston. I don't think I want to be going 90 in that truck because it shakes a lot. Okay, any questions?